Hey folks, welcome to this episode on the mole. So when we talk about particles, atoms, molecules, we're talking about things that are really small. They can't physically be counted because they're just so tiny. They have so little mass. When we talk about the mass of one copper atom, we're talking about 1.06 times 10 to the negative 22 grams. That's a really small number. When we look at a copper penny, for example, and we don't really have these anymore in Canada. And even when we do, they weren't pure copper. That would just be too expensive. But a copper penny that weighs 2.8 grams would have 1.68 times 10 to the negative 24 atoms of copper in it. That is a huge number in something that weighs so little. That's this many atoms of copper. Now, when you compare that to how many hairs you might have on your head, you have about 100,000, anywhere between 80 to 150,000. That's only this amount right here. In comparison, look at how huge that number is. So some of the hairiest people, they only have this many hairs on their head. That is nothing compared to 1 mole of anything. So when we're dealing with these particles, these atoms, molecules, whatever, we need a convenient and accurate way of measuring these tiny things, something that's a little bit more tangible. And what we do is we call this unit the mole. So the definition of a mole is 1 mole is equal to 6.022 times 10 to the 23 particles of whatever we choose to measure. Now, a particle could mean anything. Usually in chemistry it means an atom or a molecule, but it also could be, for example, bananas or pennies. It's just like saying 1 dozen. A dozen equals 12 of something. A mole equals 6.022 times 10 to the 23 particles of whatever we are measuring. Now this has many names. Sometimes it's called Avogadro's number, or sometimes it's called Avogadro constant, and it all relates to this guy over here, Avogadro, who came up with this number. And as it says here, it is one of the SI or Standard Institute units. So what kind of particles do we actually focus on in chemistry? Well, there's a whole bunch of things depending on what we actually want to measure or we're tasked to measure. Most of the things are, for example, molecules or formula units. So remember, molecules are a nonmetal and a nonmetal, or more than 2 nonmetals. Formula units has a metal and a nonmetal together, so an ionic compound. So we can measure these different things. We can also look at atoms directly. So for example, things that are by themselves, like these metals, or even atoms within a molecule. So we can go one step further here. And we can look at ions, polyatomic ions. We can treat them as a group, or we can treat them as individual atoms, whatever. So we could measure pretty much anything we'd like to. A particle is just whatever you want it to be. But these are, again, some of the more common ones we see in chemistry. So when we look at a mole, it's just like we said, similar to saying 1 dozen. A dozen means 12. So in this case, we could say a dozen particles. Now that particle could be eggs. A dozen particles would be 12 eggs. Or the particle could be roses, and a dozen roses would be just 12. Or that particle could be puppies, and we had a dozen puppies. That means we have 12 puppies. So again, dozen refers to a number, but the particles version could mean anything that we want to measure. So just like that, 1 mole, again, in terms of particles, in this case our particle is a penny, so 1 mole of pennies is 6.022 times 10 to the 23 pennies. In this case our particle is atoms or molecules, and 1 mole of these will equal 6.022 times 10 to the 23, either atoms, which is our particle here, or molecules, which is our particle here. So let's try to relate this. How big is this mole? If an atom were the size of a marble, and we had 1 marbles, and they were spread all over the surface of the Earth, our planet would be covered by 80 kilometers of marbles. So to take a look at this little graphic here. We're talking about planes, air balloons, etc., rockets. This is Mount Everest, and it's about here on this scale. And if we keep going up, well, 80 kilometers is not even on this scale. We would be so much covered in marbles, we would be crushed completely. That's a lot. That's a lot. And the whole planet would be covered in marbles 80 kilometers high. If we related it back to peas, 1 mole of peas would cover 602 Earth-sized planets 1 meter deep in peas. Think about that. 1 meter deep in peas, that if you are an average height, you'd be half covered, your whole body would be half covered in peas 602 planets over. That's tremendous. This is a really interesting one, that a glass of water, which usually contains about 10 moles of water, contains more water molecules than there are grains of sand in the Sahara Desert in northern Africa. So here is a picture of the Sahara Desert. Here's a picture of a glass. There's more water molecules in this glass than there are grains of sand in this Sahara Desert. That is crazy. Now, when we talk about a relationship between something tangible, so mass, and this moles, there is actually a relationship. In 12 grams of carbon 12, there's actually 1 mole of carbon atoms. So when we look at mass in moles, 1 mole of an element is simply the mass of that element in grams. So when we look on the periodic table and we look at one of those tiles, for example, we look at helium. Helium has an atomic number of 2 and a mass of 4. So when we look at this, the mass in grams represents 1 mole of that atom. So for 4 grams of helium, that would equal 1 mole of helium atoms. Okay, same thing if we look at copper. Okay, copper Cu has a mass of 63.55. Okay, and in that case, 1 mole of Cu atoms would equal 63.55 grams. So in the case of here, what is one mole of magnesium atoms weigh? Well, all we have to do is look at the periodic table and figure out what the mass is represented there. And when we look at Mg, that mass is 24.31. 24.31. Now, 24.31, you might see AMU, and that would be the mass of a single atom, and that's atomic mass units. But when we're talking about 1 mole of magnesium, 1 mole of Mg atoms, that's going to be 24.31 grams. Okay, same thing, 1 mole of oxygen atoms. So if we're looking at the individual, not bonded into diatomic, just oxygen atoms, again, we look into our periodic table, and we see that it's 15.999. Sometimes they say 16. So 1 mole of oxygen atoms is going to weigh 16.00 grams. So again, if you didn't have 1 mole and you had a fraction, maybe 0.5 of a mole, or 5.32 times 10 to the negative 2, for example, just a number I came up with, how much would it weigh? Well, this is what we'd have to try to figure out. We have to use some kind of conversion factor to figure that out. But one thing that will really help you in these conversion factors, and this is something we'll be talking about in the next few lessons, is you have to remember this definition. 1 mole of anything you choose, so any kind of particle, is equal to 6.022 times 10 to the 23 of that thing. So again, if we're talking about 1 mole of marbles, 1 mole of chocolate bars, 1 mole of water molecules, it will be 6.022 times 10 to the 23. So again, anything. 1 mole of anything is equal to 6.022 times 10 to the 23 of that thing. The best one is lollipops. Thanks very much for watching. See you soon, and we're going to start our calculations of stoichiometry. Take care, folks.